right, so this is Stats 3.2, Part 2, where we continue on with looking at some residual plots. So we just finished doing some least square regression lines, and now we're looking at some residual plots. And if we see a residual plot that has these type of dots to them, we can see that there is a pattern to those. That is usually a sign that our linear fit is not really a good fit. Why? Because all of the residuals are not about the same amount from the center line. There's definitely a pattern here. So we're kind of thinking maybe linear is not the best fit, okay? And that usually is because it wasn't a linear pattern to begin with. So if you go back to the original scatter plot, you should be able to see that it had some kind of curve to it. Maybe you're not sure whether it's a logarithmic curve or an exponential curve, and we really don't have to worry about that. For now, the residual plots are the ones that are going to tell us whether it's a good fit or not, all right? All right, so another thing that it can tell us that we can find is a standard deviation of the residuals. Okay, so what does this mean? So if I take a look at the formula here, we are doing the residual squared. So that's every y minus the y hat, where the line is above or below. Then we square it to make everything positive. And then we divide it by n minus 2 and take the square root. Doesn't this look a little bit like standard deviation when it was one variable? And it should, right? It's very similar to that idea, except it's two variables. So that's why it's n minus 2 on the bottom now. And what S is, it is the typical value that we would be off by when we use the least square regression line to estimate something for somebody based on the scatter plot. So it is the typical prediction error of our residuals, okay? So into our next part. So let's take a look at what it means if they ask us, interpret a standard deviation of $5,740.13 for that same truck or car example where it was mileage versus price. So they're basically saying this is S. Okay, so we're saying if I were to use or to estimate the price of this truck using my least square regression line, my price estimate is likely to be off by an average of $5,740.13. So basically we're saying my scatter plot with my best fit line of like mileage should be able to help me figure out how much I should pay for a truck. I might be off by as much as almost 50, like a little bit more than $5,700. That might be a lot. And again, it depends on the context of the problem. 5,700 over a $2 billion budget is nothing. It's really accurate. But 5,700 over a weekly grocery budget is enormous, right? So again, it depends on context there as well. All right, so let's go on and let's talk about this other R that's been floating around. So we've had R for correlation. We knew what that one was, right? So I'm going to write that up at the top here. I'm going to say R is equal to correlation. And some old-fashioned books will call it the coefficient, the correlation coefficient. Correlation coefficient. Okay, and remember that was the one that went from -1 to +1, the stronger it is, and you can say whether it's uphill or downhill. Okay, for real, R squared is equal to the correlation number squared. Okay, it really is related mathematically that way. All right, so it is also, R squared is called the coefficient of determination, which is really, really awful. And it's got this really awful formula that goes with it that is summing up the residuals on top, summing up the residuals on the bottom, squaring them each, and then doing 1 minus, okay? Well, what do we do about this? What is it really trying to tell us? So here's basically what it's trying to tell us. It's trying to tell us how much better our least square regression line is. how much better our least square regression line is for predicting y values than simply just guessing at a number. And what is that number? We're going to do a horizontal line through y bar, which is another way to say mean y. So we have a scatter plot of data, and it might be look linear and increasing as x increases, y increases. We're basically saying that the points that are more drawn, almost think of like magnetically, are closer to our best fit line than simply just a horizontal line that went through the entire graph. This is the percent that is better represented by our least square regression line. Okay, so the value of r squared tells us how much better our line is at getting y values instead of a horizontal line that is y equals y bar. Okay, now this one has a very specific way to explain it because it is a more difficult concept to understand. Again, the idea here is that I have a scatter plot, and let's say they all look like this, right? And I put in a my mean y is like right about here. So my mean y is right about here. Okay, and then my least square regression line is like, let's say here, I'm guessing, okay? Every time this point is closer to my least square regression line than it is to the y, it gets added into the percentage total. So basically I'm saying this is the percentage of dots that are closer to my least square regression line than to just the mean y line horizontally through it. So if we want to explain that, we want to say that about, and we use the percentage, so about r squared percent of the variation in y, and in this case that would be our response variable in context. So in our example, this would have been price of the car, okay, is accounted for by a linear model relating the y, which is your response variable, which is your price, to your x, which is your explanatory variable, and in context that would have been our mileage. So we're basically saying this percent of the wiggle room of the dots is better associated with our least square regression line, the linear model that's relating our mileage to price, than it is to any other line. Okay, so this is a phrase that we actually do want you to memorize about this percent of the variation. So that's usually your key idea to getting it started, this percent of the variation. So they're going to give us an example that we can practice that with. So it says interpret an R value of 0.664 in our Ford truck example. Okay, so we would start out with about 66.4% of the variation in price is accounted for. You could say is attributed to, is assigned to, is accounted for by the linear model. So I'm saying a linear is a least square regression line, right? Linear model relating price to mileage. And I am not kidding about it should be word for word. Okay, this is one that you actually do want to know and have written down word for word. Okay, and maybe I wanted to say in truck prices, right? Or Ford truck prices. All right, so 66% of the variation. So a little bit more than half are closer to my best fit line or a better fit on my best fit line than just taking the average Y and using that. All right. The other thing we want to talk about is other ways that they're going to give us ways to find least square regression line. It's really unlikely that on an AP test, they're going to give you an X and Y column and wait for you to enter it into your calculator. They're not testing you to see if you know how to do the stuff on the calculator. That's not one of the things they're going to test for, because you put in one thing wrong on your table and everything else is wrong. They don't want to have to grade that. They have no idea what you put into your calculator. So it is very unlikely on an AP test. Now on my test I could do it, But on an AP test, it's very unlikely for them to just give you 2 columns and have you start from there. What is more likely is that they might give you a computer output. Okay, and so here's an example of a computer output. I've added in some notes already. So here's what we know is when I run least square regression line on the equation on my calculator, I get y hat equals a plus bx. And we know that my calculator can't do the hat, so it will just say a plus bx. So here's the deal. A is supposed to be the y-intercept, right? In my computer printout, it is the first number. It is y-intercept. B is supposed to be the slope. Slope is the second number down here. So if I just look at the first column, it is giving me my A and my B for my least square regression line right there. I just have to know that the first number goes in the first place, the second number goes in the second place, and if you can't remember what the equation is, you look at your calculator, do linear regression number 8, and write it down from there. We're going to eventually know what everything else in this printout means, but for now, that's really the main parts that you need to know. Other things that you need to know is S. That is my typical prediction error. Okay, so this is the standard deviation of the residuals. Another way you can say this is my prediction error using the least square regression line. Okay, and we have our R squared, which really is R squared. Ignore R squared adjusteds, we don't use them. Okay, we use R squared. Now, if they gave me R squared, they're not going to go through and give me R as well because they know as well as I do that if you know R squared, you know how to get to R. You just either square it or take the square root depending on which way you're going. So I can go ahead and use those, and if I really, really needed to, I could find R from R squared. How do I do that? I take the square root of R squared. Well, remember, R squared is always going to be a positive number. I'm going to put that over here. So I have R squared is 66.4. I'm going to put it in as 0.664 equals R squared. So when I go to find R, it could be plus or minus. And if I put that into my calculator, I think it's around 0.8. My calculator says 0.815. Okay, now how do I figure out whether it's plus or minus? Well, my slope would tell me whether it's a positive correlation or a negative correlation, right? We just want to know, did the line go uphill or not? So if my slope is positive, and in this case it is, so slope is positive, then I'm going to do R is positive. So I'm going to say R is positive 0.815. And what do I know about R being a positive 8.145? That it's a good linear fit, that it's a strong relationship between the X and the Y, right? Remember those old words in describing those. Keep in mind the most important information will always be to begin on a computer output on the left upper portion of the output. Everything that you need is over here in this section, first column, and then you look and see where did they put S, where did they put R squared. Ignore any adjusted ones for now, okay? All right, so once I know that, then I can go through and I can actually write my best fit line equation by just putting it into this format and going y hat equals 38257 plus 0.16292 X, and where I would say where X is mileage and where Y is price of the car. Cool. And again, remember we talked about the other way that you could write that is you could say that the estimated price of the car is equal to, and then at the end say times mileage, instead of having to identify. If you bring new letters in, you're going to have to identify and tell us what they are. Okay, so you have to tell everybody what your X's and Y's are. They won't just assume those. Okay, so there's our first way, is just from a computer printout. The other way that they can do it is they can give us just random facts about what they know about the least squares regression line, and then ask you to come up with the equation based on that. So just random facts. So technology is probably the most frequent way they're going to do it. The other way is the sneaky way. All right, in the sneaky way, and this is on your formula sheet, which we'll have to talk about later, but it's on your stats formula sheet. Here is our first formula that we are supposed to know. Remember, B is still the same B from Y equals A plus BX, which means that this is the slope. And they are saying that slope is the R number, remember that's positive or negative, and then it gets multiplied by my change in y over change in x. Rise over run, it's just done in standard deviation of y over standard deviation of x. So it's still rise and run. Okay, the only difference is now we're going to multiply it by that correlation number. So if the correlation is 1, slope really is standard deviation of y over standard deviation of x. If r is really close to 0, then we're going to have a slope that's much, much closer to 0 because there's really not a good line in there and it should just end up being that horizontal line through the middle again. So the r, I kind of call it the fuzz factor. The further away the points are from the least square regression line, the smaller the r is, and that's going to affect my slope. Okay, it's going to move it more towards a horizontal line. So if I know that, and if they ask me to try to find a of the equation, right, then I could just rearrange these and solve for a. If I want to solve for a would be leave the y over there, move over the bx, right, and we could do that to solve for it. Also keep in mind that one of the points that they have to give you is anytime you have a scatter plot, it will go through, you can use the mean x and the mean y as a coordinate point on the graph. Okay, so this is kind of like algebra review of knowing how to find equations of lines. So let's go do one that does that. All right, so in this one it says find the equation of a line. We have x bar, standard deviation of x, y bar, standard deviation of y, and our r value. So notice they didn't give me slope, they didn't give me y-intercept. I have to go find all that stuff myself. So first thing I'm going to do is I'm going to go find the slope. So to find slope, that is b equals r times standard deviation of y over standard deviation of x. So that's going to be my 0.68, and my s sub y is 20, and my s sub x is 4. And if I multiply that out, I think I get like 3.4, something like that. Okay, so I just found slope. My next step is I need to find a, right? So I can either use this formula up above, let me change my color here. So to find a, I could use, so I need to find the y-intercept. So to do that, I could use this formula, or I could just plug it into what I know is my formula and work backwards. So I'm going to use my y equals equation, and I'm going to do point slope form. So I'm going to do, I know y must go through the y bar, so y minus 100 equals slope, which is 3.4, and then x minus what I know a point is for x, which is 60. And I could just go and solve for what that x and y would be, right? So I already know, what could I do from here? So from this, I could get directly to my equation, right? So I could do 3.4x minus 3.4 times 60, and then I could add 100 to that whole thing, and I would get y equals. So in this case, I'm going to get y hat equals negative 104 plus 3.4x. So remember, we put stuff into a plus bx format. Okay. Or I could use the formula, and the formula will make me do pretty much the same thing. It'll say y bar is 100 minus the slope, which was 3.4, times the x, which was 60, and I end up with the negative 104 that we used and found the other way. Okay, the only difference is if I go and find it using that formula, I still have to put it all together. So I just went to point slope form, not a big deal. All right. Lastly, we want you to see that when standard deviation of one variable changes because of that r value, the standard deviation of the other one is not going to change the exact same amount. So let's go and do an example of that one. So it says, if the value of x is one standard deviation below the mean, how many standard deviations below the mean will the predicted y value be? All right, so I'm going to start out with slope, right? So we know that it's still a point on the line. They're just basically saying if I were to reduce the x by one standard deviation, if I were to move the graph point around a little bit by reducing it by one standard deviation. So essentially, I would be moving my 1 point from x bar equals 60. I would be moving it to x bar number, or x sub 2 would be 4 less, it'd be like 56. So then we would want to know, well, how did y bar change? So like if y bar was at 100, how much does it go down to? And they want it as a proportion of standard deviation. So I'm thinking about in terms of like if I just slide the point over so much, how much does it have to move by? So one of the things I could do is I could just plug in the new number of 56, go calculate it through. find the new y, and then do a proportion, okay? Or I could go back and I could think about this as the formula b equals r s sub y over s sub x, okay? So basically they are saying what happens if s of x goes down 1 standard deviation? Well, this entire part of the equation has to stay the same. We're not changing the slope any, right? So if standard deviation of x goes down by 1 standard deviation, then the top part, so that would be r times s sub y, would also go down by 1 standard deviation. Okay, so if we're just talking in standard deviations, that would be 0.68. So if s sub x, s sub x is 1 below the mean, then s sub y is 0.68 times s sub y below the mean. Okay, if I wanted to actually do these in numbers, then I could actually put in the actual numbers for those and put those in as well. All right, so that's it for this one. We'll see you on the next one.